Hello dear children, in a previous class we discussed about the magnetic field around the current carrying loop. The very important thing is that how can we find the polarity of the current carrying coil. It's a very important children. So that is what we can say decided. The polarity of the current carrying coil is decided based on what children? Clock rule. That is, we are facing the coil. So that if the current is clockwise direction, then that takes south polarity. If not, if the current is flowing in anti-clockwise direction, then that takes the north pole. So that is very important. There we discussed even about the solenoid. Even dear children, to identify the polarity of the solenoid also, we are going to use the same rule, that is the clock rule only, and we will decide which end is acting like a north pole and which end is acting like a south pole. And even we discussed about what are the similarities and differences between solenoid and bar magnet. There we discussed, even after that we discussed about electromagnet. Children, what is electromagnet? Electromagnet is a temporary strong magnet. Why we are saying it is a temporary magnet, students? Because as long as the current is passing through it, through the coil which is wound around the soft iron core, then only it behaves like a magnet. The moment when we stop the current, then what happens? It behaves like a normal soft iron core only. And even how can we increase the strength of the solenoid we discussed, even how can we increase the strength of the electromagnet also we discussed. Okay, fine. Then today's class, what are we going to do? What is the today's agenda? Have a look children here. So what is today's agenda? Today we are going to discuss about the force acting on a current carrying conductor when it is placed in a magnetic field. That is the first topic which we are going to discuss. Then we discuss the units of the magnetic field. Then we discuss about Flemings left-hand rule. Children, it's very important. Flemings left-hand rule. After that we are going to get even Flemings right-hand rule also. We should not have any confusion. Okay, fine. So after completion of Fleming's left-hand rule, we are going to discuss about DC motor. Children, here one very important thing which you have to remember. What is that? Under this DC motor, we will discuss what is a DC motor, what energy conversion will take place in a motor, and what is the principle, and how can we increase the RPM, that is the rotations per minute. How can we increase the speed of the coil in electric motor we discuss. But children, the function, that working and the construction is not there in the syllabus. That we are not going to discuss at all. Okay? So under electric motor, what is the electric motor? What energy conversion will take place? What is its principle? How can we increase the speed of rotation of the coil? So these are the topics which we are going to cover in today's class. So let us start today's first topic. Force acting on a current carrying conductor when placed in a magnetic field. Children, first forget about what happens when current carrying conductor is placed in a magnetic field. First you forget about it. Let us take a simple example, children. What happens when a charge is thrown into a magnetic field? What is going to happen? Children, you might have done this actually whenever we go to the pond. Where that's a small pond, as like a water body. Okay, now with our friends, what we'll do? We'll try to throw stones into that pond. Am I right? Yes, you might have played that actually. So, dear children, what happens when you throw a stone into the water? Obviously, of course, it will sink. But dear children, at the same time, when it is sinking into the water, it experiences some force. That's the viscous forces. Of course, our discussion is not about viscous forces, but whenever you throw a stone into the water, what happens? It experiences some force. Now, dear children, in the place of water, just imagine a magnetic field. In the place of a stone, you imagine a charge. So, what happens when a charge is thrown into the magnetic field? This is very important. Now, before that, dear children, one more important point we need to understand is that, children, charge. For example, it is a charge, let us say. So, charge, for this charge, children, try to understand, V might be 0, V might not be 0. So, V0 means what, children? The charge is at rest. Very important point. For this charge, V is not 0 means what? Children, here it is in motion. What makes the difference? Children, it's very important. The charge which is at rest creates electric field, electrostatic field, electrostatic field, that is electric field. Whereas the charge which is in motion creates magnetic field, children. It's very important point. First you need to understand this point. So what happens when a charge at rest produces electric field, whereas the charge which is in motion creates, that is produces magnetic field. So now children, as I said that, you imagine in the place of water, you imagine a magnetic field. In the place of a stone, whatever you are throwing into the water, you imagine a charge. So what happens when charge is thrown into the magnetic field? As like a stone, when a stone is thrown into the water, it experiences some force. At the same time, dear children, at the same time, when a charge is thrown into the magnetic field, it experiences force actually. So this concept actually means this concept of the force experienced by the charge when it is thrown to the magnetic field is given by a scientist called Lorentz. Is called actually Lorentz. Very Lorentz. So that's what, dear children, this force, for this force only a name is given as Lorentz Force. His name is given as a Lorentz Force. Children, in exam they may ask you the question, what is a Lorentz Force? What is a Lorentz Force? Children, the force experienced by a charge, the force experienced by a charge when it is thrown into the magnetic field is called Lorentz Force. But here one condition is there. What is that condition? Charge should not be thrown in the direction of magnetic field. For suppose children, this is a magnetic field. Try to understand. Here is a magnetic field. Very, it is a magnetic field. You cannot throw a charge in this direction. Other than this, you can throw in any direction. Like this, with a certain angle you can throw, but not in the direction. You should not throw a charge in the direction or in an opposite direction. I mean what? Charge should not be thrown either parallel to the magnetic field or anti-parallel to the magnetic field. Then you may get one doubt. Sir, what happens if charge is thrown either in a parallel direction or anti-parallel direction? What happens means, I'll tell you. So, look at here. Now we'll see what happens. Here I said that the charge should not be thrown either parallel or anti-parallel. But we may get one doubt. Sir, let us throw a charge in the direction of magnetic field or opposite direction of magnetic field. What will happen? Let us see that, children. So, children, let us say here we have one charge. Its magnitude is Q and it is thrown with a certain velocity V, so that it is making an angle theta. Try to understand it, children. So, very important. Children, charge Q, it is a charge. You imagine charge. Here, let us say it is a charge. It is a magnetic field. So, we are throwing like this. We are throwing means it has some velocity. At the same time, it is making an angle theta with this magnetic field of strength capital B. Then what Lorentz says is that, definitely this charge experiences some force. Very important. So how can we calculate the force experienced by the charge which is thrown to certain velocity and certain angle into the magnetic field? Children, that is given by FB. Children, why I am mentioning here FB? The force experienced by the charge in a magnetic field. If it is FE means what? Force experienced by the charge in electric field. We are not discussing what happens when it is thrown into the electric field. Rather, we are discussing what happens to the charge when it is thrown into the magnetic field, children. So, it is experienced by QVB sin theta force. Children, here derivation is not important. Let us try to remember this formula. F is equal to QVB sin theta. Here, we discussed, we had one point. The charge should not be thrown either in the direction or opposite direction. So what happens, children, if it is thrown in the direction? Let us take in the direction. So it is in the direction of magnetic field. So as it is in the direction of magnetic field, children, theta will be 0. As theta is equal to 0 degrees, sin theta will be, sin 0 degrees is how much? 0. I mean QVB into 0 is what, children? FB is equal to 0. Oh my God. Which means what? If a charge is thrown in the direction of magnetic field, it does not experience any force. It does not experience any force. Let us see what happens if it is thrown opposite direction. Opposite direction. If it is thrown opposite, that is anti-parallel. Anti-parallel. Anti-parallel means what, children? Anti-parallel means what here? Now field is coming like this. Field is coming like this. Exactly I will throw in this direction. Exactly. I mean field is coming towards me. I am throwing opposite to the field. So what is the angle here? Angle made is 180 degrees. Angle made is 180 degrees. Then children, what is sine 180 degrees here? Sine 180 is 0 again. So when you place here is 0, QVB into 0 is 0 only. So it is FB is equal to 0. Children, very important point. I mean what? That's what Lorentz says. What he says? You have to throw a charge into the magnetic field, but not parallel or anti-parallel. I mean in the direction you cannot throw. It's the same on this one like this. So in the direction it should not be parallel. The charge should not be thrown parallel to the magnetic field. Very important. Then what happens? What happens? Nothing. As usual, it is coming. If you are throwing in the direction, simple. With whatever the velocity you are throwing, with the same velocity, happily it will go. Happily it will go because it won't experience by any force if it is thrown parallel or anti-parallel. Okay, children. So here that's what Lorentz says, that the charge should not be thrown parallel to the magnetic field. Okay, children. So very important. Examination point of view, this is very important. What is the Lorentz force? We may expect the definition. Then what we should write, dear children? When a charge is thrown into the magnetic field, other than parallel, very important, means charge must be thrown into the magnetic field but not parallel, but not in the direction. Then what happens? It experiences force. That force only we can call it as a Lorentz force. So when a charge placed into the magnetic field other than 0 and 180 degrees, it experiences force. That force only we can call it as a Lorentz force. How much force it can exert, how much force it can experience, F is equal to QVB sin theta. But when it experiences maximum force, dear children, if the charge is thrown, for example, if the charge is thrown perpendicular like this, either vertical upwards or vertically downwards, if the charge is there here, children, it is thrown like this, then what is the angle here? 90 degrees. So if theta is equal to 90 degrees, then what happens here? Sine 90 degrees will be 1. So then force will become maximum. Children, this concept is very important to understand the force acting on a current carrying conductor when it is placed in magnetic field. Children, this discussion is only about what, children? Charge. Now we will discuss the current carrying conductor when placed in a magnetic field. Okay, first you copy this, we'll proceed. Now children, look at here. So children, let us say it's very important. Let us say it is xy. Of course children, here is continuation is there just before x and after y. Okay. Children, what is xy here? Xy is a current carrying conductor. Children, it is a current carrying conductor and its length is L. It's very important, children. So current carrying conductor, its length is L and through which I current is passing. And it is placed in a magnetic field of strength B. So that it is making an angle theta. Children, it's very important. Current carrying conductor of length L through which I current is passing is placed in a magnetic field of strength B with an angle theta. Then what will happen? Children, just now we discussed what happens when a charge is introduced into the magnetic field. Of course, their cases are there, not parallel, not in the direction of magnetic field. So we have learned that charge experiences force. Children, now think about this conductor. Conductor means through which what is happening is not simple conductor, through which current is passing. Now you tell me, children, what is the current? Rate of flow of charge. I mean, can we imagine a situation like this? All charges which are moving in a disciplined manner, through a conductor. Of course, that only when charges will move in a particular direction, then only we can call it as a current. As current is passing through the conductor, which means what? Can we imagine that charges are flowing like this? Yes, through this actually charges are flowing. Means in the previous case, one charge is flowing. Now in this case, many charges are going. So what happens? Obviously children, it experiences force. Why? Because through the conductor, charges are flowing. When charges are introduced into the magnetic field, it experiences force. And even ICSE also explain the same thing. Current carrying conductor produces magnetic field. Children here, look at this, very important. Let us say it is a current carrying conductor. Through this current is passing, and around this what will be there? Magnetic field will be there, children. Magnetic field will be there. Now, can I assume it as a magnet? Of course, yes. Children, come on, think. It is a current carrying conductor. It produces magnetic field around it. Now, as it is producing magnetic field around it, can we say it is a magnet? Yes. What happens when this magnet is placed in a magnetic field? When magnet is placed, one magnet is placed in another magnetic field, what happens? It experiences force. It might be attractive force or repulsive force, that you leave it. But children, definitely what happens, when current carrying conductor is placed in magnetic field, it also experiences force. Okay. But on which factor does it depend? Children, it's very important examination point of view. So, it depends on actually 4 factors. Very important. What is that? First factor is that, children, the force experienced by the current carrying conductor is directly proportional to the magnetic field strength. I mean what? If this magnetic field strength is more, then obviously it experiences more force. If the magnetic field strength is less, it experiences less force. And the second point, this force experienced by the current carrying conductor is directly proportional to the current which is passing through the conductor. Children, if more current passes through it, what will happen? According to ICSE experiment, more field is generated, which means what? It experiences more force. So, it also directly proportional to the I only. And the third one, children, very important, F is directly proportional to the length of the conductor. Children, as length of the conductor is more means what? The number of charges in presence of magnetic field will be more actually. The length is less means what? Example, in this length 100 charges are there, let us say. The length is doubled. The number of charges will be increased. As the number of charges will be increased means what? The force experienced by each and every charge will be increased. Which means what? So here the length of the current carrying conductor which is placed in a magnetic field also matter here. There are 3 factors. What about the 4th factor? Yes, it is angle. Very important. Here angle also matter. So the force experienced by the current carrying conductor when it is placed in a magnetic field depends even the angle also. Angle between what, children? Current and the magnetic field. So this we can write like this actually. F is proportional to the BIL, and here F is equal to, let us take one proportional constant, it is BIL. Whatever this K value. So K is equal to, we will take as a 1. Here you should get a 1 down. Sir, why we should take a K is equal to 1 actually? Children, it's a very clear that force is depending on these 3 factors, and even we will assume that it may depend on another factor also. It may depend, it's assumption. It might be, it might not be. And we are assuming that it is a K. Force also depends on K. And we will do the experiments, we will repeat the concepts. And we here, especially in this case, we came to know that this force acting on this current carrying conductor does not depend on any other factor other than these 3 here. So, its value will take as a K is equal to 1 actually. So, finally, here we will get F is equal to BIL. This is a magnitude, children. It is a magnitude actually. But in a higher classes, children, in a higher class, a very important thing is that in a higher class, we will discuss even vector form actually. Of course, in this standard is not needed, but actually we will get F is equal to BL is a magnitude actually, but we get F is equal to, this is actual formula is BIL sin theta here. What is theta, dear children? Theta is a angle between current and the magnetic field. This is a very important to understand. Theta is the angle between current and the magnetic field. Okay children, so this is how actually we can calculate the force acting on a current carrying conductor when it is placed in a magnetic field. But here we may get one question. When this force will be minimum, when this force will be maximum? Children, let us see here. When this force is going to be minimum, when this force is going to be maximum is very important. So let us take here. If theta is equal to 0 degrees or 180 degrees, which means what here children? If this conductor, actually it is placed like this. If it is placed exactly in the direction of magnetic field or opposite direction to the magnetic field, in that two cases it will be 0 and 180 degrees. Then what will happen? Sine 0 degrees or sine 180 degrees is equal to 0 only. Then what will happen? Force will be minimum, that is 0. Children, it's very important. In exam they may ask the question, when current carrying conductor experiences minimum force when it is placed in a magnetic field. So simple thing we should write. It's a one word answer. You should write that when current carrying conductor is placed in the direction of magnetic field, it experiences minimum force, that is 0. And the second point is that if theta is equal to 90 degrees, which means what children? This conductor is placed like this. Try to understand, either like this or like this. Then what will be the angle? Angle will be 90 degrees, means when a current carrying conductor is introduced perpendicular to the magnetic field, theta is equal to 90 degrees, and we know that sine 90 degree is equal to 1. So force will become maximum is how much children? BIL. Force will become maximum. So when the force will be minimum, when the force will be maximum is very important children. When current carrying conductor is placed in the direction of magnetic field, the force acting on that current carrying conductor will become minimum, that is 0. Whereas when it is introduced perpendicular to the field, then what will happen? It experiences maximum force, that is BIL. Now children, here this discussion is very important. Here B only called what? Magnetic field. Children, here examination point of view, the units of magnetic field are very important. Now we will see units of magnetic field. Units of magnetic field. Children, the expression which we got, the magnitude of the force, the maximum magnitude of force experienced by current carrying conductor when it is introduced into the magnetic field is F is equal to BIL. Let us make B as a subject, that is B is equal to F by L. F by L. Now let us see. Children, we know that F is measured in Newton, current is measured in ampere, length is measured in meter. Now let us write for a B. Then for a B, units are Newton per ampere meter. Children, very important. What are the units of magnetic field? Newton per ampere meter. Children, this Newton per ampere meter is also called as Tesla. It is also called as Tesla. So we can write as it is also called as Tesla. So the symbol is capital T. And children, this Tesla is also expressed as Weber per meter square. Weber per meter square. Children, actually Tesla is a SI unit of the magnetic field. Then what about CJ's unit? It is called Gauss. So it's very important. This is actually SI unit. The CJ's unit of the magnetic field is Gauss. Gauss, Gauss. Okay. So how these two are related? 1 Tesla is equal to 10 to the power of 4 Gauss. Children, very important relation. That's it. So examination point of view, direct question is, what are the units of the magnetic field? Children, mostly actually according to this concept, we will use this only, Newton per ampere meter, but it is also called as Tesla. Tesla is nothing but Weber per meter square, and even it has its Tesla is a SI unit, the Gauss is a CJ's unit. 1 Tesla is equal to 10 power 4 Gauss, or 1 Gauss is equal to 10 to the power of minus 4 Tesla. Okay children, so this how. Okay, and here we will get one doubt actually. Okay sir, when a current carrying conductor is placed in a magnetic field, it experiences force. So how much force means? F is equal to BIL. But children, here force is a vector quantity. So this is actually magnitude. but how to find the direction of force acting on a current carrying conductor when it is placed in a magnetic field. Children, it's very important. I repeat once again. What is a force? Means we know that when a current carrying conductor is placed in a magnetic field, it experiences force, but how to find the direction of magnetic field? Children, for that the answer is given by what? Fleming's left hand rule. Now let us discuss what is a Fleming's left hand rule, children. Left hand rule. So children, Fleming's left hand rule. In exam directly they will ask you the question, what is that law or rule which is used to find the direction of force acting on a current carrying conductor when it is placed in a magnetic field? So the answer is Fleming left hand rule. Now let us see, the children, what is this Fleming's left hand rule? So for this, children, come on, take your left hand. Take means not completely removing and taking with your hand. It's not that. So take your left hand such that, children, look at here. It is central finger, forefinger, thumb finger. So these three should be arranged. Mutually perpendicular to each other. Okay, now after arranging this like this, children, if central finger shows the direction of current and forefinger shows the direction of magnetic field, then thumb finger will give the direction of force acting on a current carrying conductor when it is placed in a magnetic field. Then children, how to remember this actually? For this we have a simple trick actually. Look at here. So these three fingers, try to understand here. So first one is central finger, then M letter is highlighted. Children, C represents current. Forefinger, F represents field. That is magnetic field. Then M represents motion of the conductor. Children, it's very important. Logically we have to think. If one object is moving in one direction, means what? In the direction only force will be acting. So motion of the conductor, the direction of motion of the conductor is nothing but what is, children? Force direction. So M represents here motion or force. Children, try to understand. Always the body will have motion in the direction of force. So the direction of motion means what? Direction of force acting on a current carrying conductor. Children, this is very important. Now children, with the diagram we will see, then we will understand. Okay children, let us see with the diagram so that it will become very easy to us. Out of the board. So look at here. Children, it is case 1. Children, to understand Faraday, it's very important. It is case 2. Fleming's left hand rule, not Faraday, sorry. Fleming's left hand rule. Children, look at here. So here also magnetic field strength is capital B only, and here also magnetic field strength is capital B only, and its length is L on same only. Children, try to understand. So here what is this dots and what is this cross? Children, here actually we have one sign convention, children. So whenever we are discussing about the magnetic field, for sake of our comfort, we have a sign convention. Here into means what, children? You should understand that magnetic field is going into the board. See, very important. This magnet means all field lines are from you to they are going towards like this. All are going like this into the board. Whereas in this case, in case 2, dots are there, which means what? Magnetic field lines are coming out of the board, children, like this, straight they are coming. Now they are coming towards you, right? It's very important. In 2 cases. First we will see in this case, dear children. So here it is a current carrying conductor. Okay, now its length is L. It is placed in a magnetic field B only. And it's very clear that Fleming left hand rule says that actually Lorentz says that actually according to the Lorentz concept, force will act. In which direction? Fleming's left hand rule will give. Come on, let us apply the Fleming's left hand rule. Chill, look at here. So central finger, C for central finger, C for current. So this should be in the direction of current, okay, in the direction of current, okay. But here forefinger, F for field, should be in the direction of magnetic field. So in the direction. So look at here, try to understand. So this is in the direction of current and this is into the board, children. Try to understand, it is into the board. Then thumb finger, children, look at here, very important. So My forefinger I have shown into the board because in the direction of magnetic field. Field is in the direction. Central finger is in the direction of current. The thumb is showing vertical upwards. I mean what did children here? Upwards. So force is acting. How much force? F is equal to BIL force is acting vertically upwards, children. Vertical upwards. Very, very, very important. So in this case, force is acting. Thumb is showing vertical upwards. So which means what is children? If field is into the board, current is going right side, okay, then force will be upwards. Children, in this case children, how the force will act? Come on, you think. Apply the Fleming's left hand rule, you think, and mention the direction of force in the comment box. Children, just pause the video. Children, you have to do it. Unless you do it, children, you won't get the grip on the concept. Come on, apply, just pause the video and try this. In this case, how the direction of field will be. So just think about it and mention in the comment box. Okay, got it? Come on, think. Okay, so current direction, come on. What is central finger, current direction? But by this time, field is coming out of the board. Coming out the board means like this. Try to understand. So look at here. So field is towards you. Field is towards you. Current is right side only. Now in this direction, look at here. So children, so central finger is indicating, showing the direction of current. Forefinger is showing the direction of field. The thumb is downward direction. Thumb is downward direction, which means what? In this case, force F is equal to BIL will act, but downwards. Downwards. Very, very, very important. Which means what, children? Which means what? When you can change the direction of magnetic field, the force acting on current carrying conductor also changes. These are very, very, very important. Children, this is a very important. What is actually Fleming left hand rule? What is the purpose of Fleming left hand rule, dear children? Fleming left hand rule is used to find the direction of force acting on a current carrying conductor when it is placed in a magnetic field. How much force means, how much maximum force means? F is equal to BIL. But who will give you the direction? Fleming left hand rule. Fleming left hand rule. Children, this Fleming left hand rule is very important in order to understand the principle of working of electric motor. Just you copy this. We will move to the electric motor. Okay, fine. So fine, children. Now we'll see what actually simple DC motor, children. This is very, very important. Children, what is a DC motor? Children, the device which converts electrical energy into mechanical energy is called simply DC motor. Simply motor, let us say. So in exam they may ask you the direct question. What is DC motor? What is motor? If they'll ask you what is motor also, you can write that a device which converts electrical energy into mechanical energy. If not, children, same point can be asked like this. What energy conversion will take place in electric motor? Then what you should write, children? You should write like this. So electrical energy. So electrical energy to mechanical energy. That's it. This is what actual electric motor definition, and what energy change takes place means. So the energy change takes place is that electrical energy is converted into mechanical energy. Children, again I am telling you, in the syllabus, the working, the construction part is not there. Construction part is not there. This definition is very important, and at the same time here, the principle also very, very important. Now we will see the principle of working. It's very, 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 very important to understand. Principle. Children, let us take here a rectangular copper coil. Rectangular copper coil is taken like this, children. Rectangular copper coil is taken. Try to understand. So here, let us name it as A, B, C, D. A, B, C, D. Fine. Children, let us see. It's a rectangular copper coil through which current is passing. Okay. Let us assume that the current direction is like this. A to B, B to C, C to D, D to A. Like this. D to A in this direction. Let us take. Children, as I said, it's a rectangular current carrying copper coil. Rectangular current carrying copper coil. Now, can we assume it as the combination of 4 conductors? 4 linear conductors? Obviously we can. AB is a one conductor through which current is passing. BC is a one conductor, CD is a one conductor, and it is a one conductor. So 4 conductors are there. And children, when current passes through a current carrying conductor, what happens? Let us recall about the Oersted experiment, Oersted concept. Children, current carrying conductor produces magnetic field. Means what is children? A to B is a conductor, yes, magnetic field will be there. What will be the direction children? The direction of magnetic field around the current carrying conductor is given by right hand thumb rule, come on, right hand thumb rule, which means what? Here, thumb should be in the direction of, assume that current carrying conductor is held with the right hand, such that thumb shows the direction of current, then field will be like this. I mean what, around this AB, the field will be in this direction, field will be like this. Whereas BC, field will be like this. Around CD, field will be like this. I mean what? Field will be in this direction. So similarly, around the AD also. Means what? Each and every side of the current carrying, what we can say, coil, is behaving like a magnet. Children, each side is producing some magnetic field. On each side there will be magnetic field. Means on whole, obviously magnetic field will be there. Which means what, children? Current carrying rectangular copper coil produces magnetic field around it. Obviously, that we know very well. So whenever current is passing through either the conductor or coil, definitely there will be a magnetic field. Children, now around this total magnetic field will be there. Now my point is as this entire setup, dear children, if it is placed in a external magnetic field, you think that children, you think, so here, let us think children, it is a just rectangular copper coil, rectangular current carrying copper coil. When this rectangular current carrying copper coil, around this magnetic field will be there, don't forget that. And this entire setup is placed in a magnetic field. What will happen? Children, what will happen? So, let us think the direction of magnetic field. I mean what? For example, children, this side, one magnet is placed with the north pole, and here also, children, very important, another pole, concave shaped magnetic field, so as to have radial and uniform magnetic field, uniform magnetic field. Now, how the magnetic field direction will be there, children? We know that it is always north to south. Why it is not writing? Children, it is a north to south. So, this is the direction of magnetic field. Children, this is the direction of magnetic field. Now, children, try to understand. What will happen when current carrying rectangular copper coil is placed in a magnetic field? Children, let us recall before this, today's first topic, what was that? What happens when current carrying conductor is placed in a magnetic field? Obviously, it experiences force. How much force it experiences? BIL force. How to find its direction? With the help of Fleming left hand rule. Now, dear children, this discussion also we will see. A to B is a conductor, B to C is a conductor, C to D is a conductor. Let us discuss what will happen. Obviously, on AB, children, if this side is, let us say, L, and this side also L, and this side is B, and obviously this side also B. Now, what will happen? Let us see, children. Obviously, on AB, through AB, so A to B is a one conductor through which current is passing. Where it is placed in a magnetic field, obviously, some force will act on this AB side. How much force will act on AB we will discuss now. Now, children, force acting on AB side will be, what is the formula? BIL sin theta. But theta is how much, children? Look at here. This is a magnetic field and it is. So, this is 90 degrees. So, sin 90 is equal to how much, children? Sin 90 is 1, or else let us write step by step BIL sin 90 degrees. So, sin 90 is 1. So, FAB, children, the force acting on AB side is how much? BIL. Okay, it's fine. It is fine. Now, let us discuss how much force is acting on BC side, children. Same formula, BIL sin theta. But children, here what is the angle? See, field is in this direction only. Current also is in the direction only, which means what? Both are parallel. Theta is equal to 0 degrees. That is BIL sin 0. Children, sin 0 is equal to how much? 0. So totally 0. So how much force will act on BC? 0 force. No force will act. No force will act. Now let us discuss third side, that is force acting on CD. Force acting on CD, same formula BIL. Children, here the side is B actually. Let us take a B. Okay, here B only. Here is a BIL. This length is L only. This length is L sin theta. Children, in this case also, see, field is in this direction, but whereas the current in the CD is downward direction. So what is the angle here? 90 degrees. That is, look at here, it is BIL sin 90. So sin 90 is equal to how much, children? 0. So force acting on CD side also BIL. BIL. Now let us see the fourth side, that is force acting on AD. Force acting on AD, BI. This length is B sin theta. So it is BIB. Children, current is in this the field is in this direction, north to south, but the current is flowing in opposite direction. That is 180. Sin 180, children. So sin 180 is 0. So obviously force acting on AD will be 0 only. Very important. Very important to understand. Just copy this detail, children. Next we will proceed. So children, with this it is very clear that no force is acting on BC and AD. You forget about the two sides. The force acting only on AB side, CD side. So very important thing is that, children, same force is acting on BIL force, and here also BIL force, same force will be acting. But dear children, in which direction the force is acting on AB side and CD side? Now let us discuss. How to decide the force acting? Fleming left hand rule. Come on children, come on. Fleming left hand rule. Come on, place central finger, forefinger, thumb finger, so that three should be mutually perpendicular to each other. Children, current direction upward. Oh my god, current direction is like this. But field is like this. Okay. Oh my god. Yes, fine. Okay, come, no problem, not an issue. So, but of course, it is better to this only. Like this, field, current. Yes, children, try to understand. It is like this. So, field direction, forefinger, field direction. Okay, now central finger, current direction. See, in AB, current is flowing upwards, but thumb is showing into the board, children. Means the force acting on AB will be into the board, children. Into the board, I am putting like this. This symbol indicates force acting is into the board. Try to understand. Very important. Okay. Now BC AD, no headache because no force acting. Now come to the CD. On CD, the force is acting F is equal to BIL, but in which direction? Let us see here. So it should be in the direction of current. Children, try to understand. Central finger in CD, downward direction. This is forefinger in the direction of field. The thumb is showing out of the board, children. Out of the board. So here force is acting out of the board. Children, look at very important. Which means what? Let me take this example. Children, if it is a current carrying rectangular copper coil placed in magnetic field. So here this side no force, here no force. Here the force acting is into the board. Here this side force acting out of the board. Children, two equal forces in a first chapter called force. There we discussed on a body at two different points. Two equal forces are acting on a body in opposite direction. Then what will happen? Body will be rotated. Means there will be a couple. Children, in this case, one more very important question. What is the net force acting on the current carrying coil here? Rectangular coil. 0. Why? Two equal forces. F is equal to bill. One is into the board. Here out of the board. Both equal and opposite forces are acting. Means net force is 0. But there will be a couple. There will be a torque which causes a rotation. So here, look at here. On this, at this side AB, force is acting into the board. Here the force acting out of the board. Then what will happen? This coil will be rotated. So by doing some arrangement setup, children, what we'll do? We'll make the coil to rotate continuously. Children, this is a principle of working of electric motor. Over. Khatam. Finish. Simple, it's as simple as that, as simple as that. So let us recall children, in exam, if they ask you to write the principle of working of DC motor, you no need to explain all these things actually, it's for sake of our understanding. So what we should write? When current carrying rectangular copper coil is placed in a magnetic field, it experiences torque, it experiences couple, due to which it is rotated continuously. Children, note down, it's very important. When a current carrying copper coil is placed in a magnetic field, it experiences couple, due to which it is rotated continuously. It is rotated continuously, so that electric energy is converted into mechanical energy. Electrical energy is converted into mechanical energy. Children, for this only, we will do some arrangement setup. Look at here. So, how the children, hope you have copied this. Now, let us see that how the arrangement setup of the electric motor, children. So, here for this only, look at here. So, this is here, two commuters will be there. So, children, this is how actually circuit will be. So, what are the main components of the electric motor, children? Concave shaped magnets, which produces what we can say a radial, a uniform magnetic field. Children, so one more very important thing, here is a uniform magnetic field only. In a higher class, you will be learning what happens when a copper coil is placed in a non-uniform magnetic field. Children, when a copper coil is placed in a non-uniform magnetic field, it will move. It will move. But whereas when current carrying copper coil is placed in a uniform magnetic field, it is rotated. Why? Because two equal and opposite forces will act. There will be a couple. But children, the net force acting on the current carrying copper coil when it is placed in a magnetic field, that is uniform magnetic field, is how much? 0. No net force, but only couple will be acting. So here ABCD is a armature, that is a coil, and here C1, C2. Children, C1, C2 are called actually what we can say half split rings, are called commutators. In exam, they may ask you the question, what is the purpose of commutators? Children, commutators are the rotating devices which are used to change the direction of current for every half cycle, for every half rotation of the coil. Very important. So, what is the purpose of these commutator, children? These are the rotating devices which are used to change the direction of current for every half rotation of the coil. So, here B1, B2 are the carbon brushes which makes a contact so that circuit is completed, and here is the battery and this is the key, here is a rheostat. Children, the working of the electric motor is not in the syllabus, that we are not going to discuss. Okay, fine. Okay, and it is rotated in the magnetic field and there will be a shaft. Means this entire copper coil is mounted on a rod which is called shaft, children. So, which will be rotated means the shaft is this is called actually shaft. Children, the shaft is utilize the mechanical energy so produced. Means copper coil is rotated, the shaft also rotated. So, for this let us arrange three wings like this. So, that wings also rotated. That's simple to understand, Okay, children, fine. Now, we will see on which factors does the rotation of this copper coil depends, or else. So, let us see how can we increase the rotation of the copper coil. Children, it's very important examination part of it. How can we increase the speed of rotation? How can we increase the speed of rotation of the copper coil, children? It simply depends on 4 factors. Just you can remember this, children. So, here RPM, rotations per minute of an electric motor, depends on 4 factors. Simply you can remember like this: A nib you can remember, okay na? Here, so children, here rotations per minute of an electric motor, that is a coil, depends on 4 factors. Just you remember this clue, A nib, so that you can understand that. A represents what? Area of the coil. N represents what? Number of turns of the coil. I represents what? Current, that is the magnitude of the current. B is what, children? Magnetic field of sun. I mean what, children? By increasing either of one, children, by increasing either area of the coil, number of the turns of the coil, current and magnetic field strength, you can increase the rotations per minute of an electric motor. Okay, children. So these are today's topics, children. Okay, now once let us recall what we have discussed. Children, beginning we discussed about Lorentz force. After that we discussed about what happens when current carrying conductor is placed in a magnetic field. And there we discussed about Fleming's left hand rule. Children, what is Fleming's left hand rule? Fleming's left hand rule is used to find the direction of force acting on a current carrying conductor when it is placed in a magnetic field. And even we discussed about the units of the magnetic field. So, it is a very important examination point of view. Then we discussed what is electric motor, its principle, and finally RPM of an electric motor. Children, next class we discuss about the very important, that is what actually Faraday's law of electromagnetic induction. Children, it's very important. Means here actually electrical energy to mechanical energy, electrical energy to mechanical energy. Of course, it produces magnetic field. But next topic we are going to discuss about actual magnetic or electromagnetic induction, where we are going to discuss how a magnetic field produces electrical energy. So there only we will discuss about AC generator. Children, that is quite opposite to this electrical motor. Actually, electric motor converts electrical energy to mechanical energy, whereas generator converts what is, children? Mechanical energy to electric energy. So that will be discussed in a next class. Thank you so much, children. All the very best.